before we fix effect versus a random effect. So that's why there are a lot of tests for us to test whether we should use the random or should use the pool. So in such a scenario, here is used to test if to test whether the pool OS versus the random effect. So actually, if go back to the pool OS, right? Actually, we should not have this individual residual, right? Because under these random effect models, we have a two component. One is a cross-section random, another one is a idiosyncratic random. So if we do not have this cross-section random, it means that when this one equals to 0, actually it will go back to the pool OS. Right? It means that you will have, because still remember how we test the equality of the intercept? We restrict, right, the coefficient for the intercept at equal. Because we have an individual intercept. But under this random, we are more concerned about this cross-section random, which is random, right? It's used to capture in the what we say composite. It means the algorithm. One is the U, the other one is epsilon IT. Add together become the VIT, right? So if this we cannot avoid one. Idiosyncratic random is inside the model itself. But this cross-section random, which is just inside this random effect models, which is the U here. If this one equals to 0, actually is go back to the pool OS. Right? If we choose between these two models, so actually it's testing this one. Sigma power means refer to the variance for this random errors. It means that this effect residual equals to 0. Equals to 0. So if equals to 0, it means that actually is preferable to the pool OS. So now, actually we have several tests. Besides equals to 0, actually another word is no individual effect, no time effect, no individual and time effect. It means that the pool OS, right? It means that no individual effect. So we are testing. So what we are testing is based on the pool OS residual. We have to use the pool OS residual. So when you want to test this, for example, by using the means that compare between pool OS together with the random effect, we have to use the pool OS setting. Pool OS setting in the pool OS estimation. Then from there we test this hypothesis whether there should be a individual effect inside in our estimation. So the original means that the original statistic, right, is actually Bush-Buchan Lagrange multiplier statistic. Then after that is extended because you can see the years, right? Bush-Buchan Lagrange multiplier. In my years, I first start to learn about this Bush-Buchan Lagrange multiplier, which is 1980. Then after that is extended because of this what we say because just like the usual test, right? We have the NDF, we have the PP, and we have the KPSS. Because of this something like discussion in the literature, so we have so many complementary statistics to check between the pool OS or the random effect. So we have a much more statistic coming in there. Together, I think the latest one is not the latest lah. I think you can see the years, right? Because in 1999, Baldacci et al. Extend the Bush-Buchan, Honda, King and Wu. This 1, 2, 3, 4, 5. This 5%, right? Come up with the test, with the considered latest test, but the Baldacci et al. 1999 extend it to take into account the unbalanced design. Because in the panel we have a balanced panel as well as unbalanced panel, right? We cannot avoid because in the panels, why I want to use a panel because of this some data set actually is not available. Full set, the data set we use in our exercise is a balance. That's why no missing, right? No missing value. But some data set actually is imbalance. For example, because of some data set is not available for certain recent years, right? Because of we have a few variables, right? So maybe one series is maybe just have a lesser year compared to others. So we have an unbalanced panel. That's why unbalanced panel we have a different statistic. Because it's based on statistic, right? You can see the formula here. is based on statistic. So if let's say, and also based on the mean, right? You can see there's a bar here, right, based on the mean. If let's say different sample, right? Because of the T, different sample, so that's why unbalanced panel a little bit have some challenge lah when you want to test for the unbalanced panel. So for the balanced panel, it's original one proposed by grand multiplier. And for the unbalanced panel, right, they have a different approach to take into account the unbalanced panel. So that's why I have some discussion in the literature why we have a different type of statistic to test between the random effect together with the pool OS because of this because of this unbalanced panel, and also some adjustment in the test statistic. Let's say maybe some of them claim that my test is much more powerful compared the earlier test. So I come up with the recent test. This is something like the chronology, right, for this development of this test statistic. But the purpose is test between whether it's a random versus the pool OS. Okay, so you can go through the paper lah, right? You want to know more, right? So actually, like the Honda is a one-sided alternative to get the much more powerful test statistic. It's the most powerful in the year 1985. Yeah, we say it's the most powerful one, uniformly most powerful statistic. And then this Honda and Red Road, another test statistic on the improved version asymptotic signs. So there's a different, right? Different power of the test statistic compared to the earliest version. Okay, so how are we going to apply this statistic, right, to test pool or the random effect? So you can go to again, as I mentioned just now, it's based on the pool as setting. So you have to go to when you estimate, right, you have to go back to the conventional one. When the cross-sectional, you have to untake, become none, because I want to see whether the sigma power 2 for the U is it equals to 0 or not, right? So I want to check on that. So I want to see whether there is an individual effect. So cross-section, you choose none. Then you go just conventional one, just run the pool as regression. Then from here, you go to view. From here, you go to view, because if you check for random, you cannot run the test statistic. If you check for fixed, you mean you can take the fixed effect model, you cannot run this test statistic. You have to be in the pool or S setting. So go to view, and then check fixed or random effect testing. Choose the Lagrange multiplier, omitted random effect. So I want to see when I omitted it, significant or significant. If significant, means I cannot omit it. That is the thing. Okay. So under the now, no effect. Right. This is my result. Under the now, no effect. So in the pool or S setting, when I estimate the pool, right? Then go to the view, go to random fixed effect testing. Choose the omitted random effect. Choose the omitted random effect, Lagrange multiplier. That's used to check whether got effect or no effect. Okay. So this is the Lagrange multiplier for random effect because I want to choose if the test significant. So reject no effect, then is prefer random effect models. Okay. So now are they significant? So based on the Busch-Backus test, the original one. In the parentheses refer to the p-value. So this is a test statistic. So this is a cross-section. And then this is a individual time, cross-section time. And then boom. Actually, all the tests shows that they are significant, right? They are significant. So you tend to reject the Hirschsprung. So this prefer the random effect, right? Under this scenario, prefer random effect. Then how about Honda? Honda test is proposed by Honda. Then Honda statistic will be cross-section, reject. It means there is a cross-section. When I allow for, it means that test for the cross-section, because we have two ways, right? Remember, we have two ways. One is cross-section with the time, or both, right? So if I just test for this cross-section, actually all the test statistic, even though it's King Wu or standardized Honda, or this latest one, right? Standardized King Wu and so how to spell it? Glorious. Okay. Okay. All this one is not available. All significant. Right. Given the p-value, all significant. So you tend to reject the Hirschsprung of no effect. It means that pool S is actually proven that not accurate, right? Not accurate in this scenario. So I will choose between the fixed effect, right, versus the random effect. So here, pool versus the random. So I can make my decision based on this result. So I can stick not here. So the result here shows that what we say. When I check for the pool versus the random, the result significant. All the results significant, right? So you reject. So you reject the first now. So now it's favor to random effect model. Oh no, this random effect model in the previous result means based on the wall test fixed effect model, right? When I use the wall test pool versus fixed, so it selects the fixed. When I do the second test based on the set of tests, pool versus random, is prefer random. So now, random or fixed? Random or fixed? So it's time for us to test random or fixed. Okay? So which one you will choose? For this random or fixed, yeah, you can use the Hausman test. So in actually is decide the models fixed effect versus the random effect. Which one is better? Do you still remember? I keep on emphasizing on one statement. If there is a correlation between this the effect, right? It means that between the random effect together the independent variable, we should choose the. It means if there is a correlation, then we cannot choose the random. We have to use the fixed effect models. So that is the things we want to test. So this one also called Durbin-Wu-Hausman test, okay? In short, it's a Hausman in 1978. It's still real recent. It's still, I don't think got another test to replace it. It's still when you read the article I share, you still use the Hausman test to test which one will provide you much more efficient estimator. Actually, it's compared between the estimators, okay? So it's compared between this estimator, fixed effect and random effect to see whether which means efficient or not efficient. So this is the test set. This is a test set. Details of the test. Okay, details of the test. So again, you can see the second segment here. So if there is a correlation between the individual effect and the regressor, then which one is preferable? GRS and inconsistent. If there is a correlation between the individual effect and the regressor, we cannot use random effect models. So that is a statement here. Because estimate become inconsistent. Estimate become inconsistent. So we cannot use the random effect model. If this assumption by random effect model, right? If you want to use a random effect model, you have to make sure there is no correlation between it means amongst the individual effect and the independent variables. If this assumption warranted, we cannot use random effect. So what model we can use? Fixed effect. Because we are testing between the fixed and random, right? So that is the thing. So you have to construct a test statistic, then form your test statistic. So this is a test statistic. Actually, what you need to know is significant, reject it, then we have to use the fixed effect model. So it is just want to test the consistency between these two estimated. So under the Hirschsprung, we have the Hirschsprung, right? Hirschsprung is random effect are efficient versus the alternative fixed effect inefficient. Means that actually is same, right? So under the Hirschsprung is random effect are efficient. Okay, random effect efficient because it's statistic, right? We have to understand the Hirschsprung. So what is the it means that the degree of freedom for this test statistic? K minus 1 degree of freedom. Okay, K refer to the number of regressor. So when to reject? If your test statistic lesser than the critical value, random effect model is preferred. So it means that if you fail to reject, random effect is preferred. So if not significant, then we prefer the random effect because random effect estimator provide us the consistent estimate. Consistent fixed effect are consistent. So if you want to choose between the random effect and fixed effect, you have to see whether your test is significant or significant. Okay. So let's say how to choose. In our situation, we have to estimate first. Okay. We go to estimate. Now you have to estimate the random, right? You have to estimate the random effect models. Estimate the random effect models. Then you go to view. Fixed effect testing. Fixed or random effect testing. Correlated random effect Hausman test. Yeah. So if you estimate based on the fixed, right? I don't think you can get this Hausman. Let me see whether you can get it. No, cannot. So the test require with the random effect. Okay? Because we have to track the random fixed effect, right? Random individual effect, right? So you have to choose this one, cross section become random. Then you only can test the Hausman test. You go to view, because it's different model, right? You go to view, then go to random or fixed effect testing, choose the Hausman test. You choose the Hausman test, so this is the test statistic. So choose the Hausman test. So how we decide reject or not reject? So if the Hausman test less than critical value, we cannot reject. Then because both models are consistent, but the random effect estimate are much more efficient, so we choose the random effect. So if you feel to reject, then random effect model is much more reliable compared to the fixed effect. So now, is it feel to reject? Yes. You feel to reject, right? Yes, because you feel to reject. So now your result is feel to reject. So this is our statement, right? Because they compare, right? They compare the fixed effect coefficient together with the random effect coefficient. Right? The test statistic compare, right? Compare the coefficient, these two coefficients. This from the fixed effect model, this from the random effect model, and then the difference. Do you remember the formula just now? The formula for the Hausman test, right? Is like this, right? The difference. Different, and then they complete the test statistic here. So this one not significant, right? Not significant. If you compare with the critical value table, also not significant. You can compare with the chi-square critical value table. The degree of freedom 2, I think somewhere around like 5.99, like 5%, like 5.9 or 1 at 5%. So it's lesser than the critical value, lesser than 5.91. No, it's bigger than at 5%. So cannot reject. So actually they are consistent, but it's random effect are efficient, much more efficient as compared to the fixed effect. So we choose the preferable is fixed effect model. Sorry, random effect model. We will choose the random effect model. Based on the Hausman test, okay? So alternatively, you can refer to this p-value. In the emails, it's also provide you together with the p-value. If you don't want to compare with the what we say statistical tables, if the question, for example, in the final exam, right, we will provide you the statistical tables, right? You have to choose the critical value by yourself. If the question high enough, they will provide you together with the p-value. So you can straight away draw a conclusion based on the p-value, and it's based on 5%. This p-value actually greater than 0.05. So feel to reject, right? Feel to reject. So feel to reject. So once you feel to reject, you will prefer the random effect model. So it means that at the end, you have to report the random effect model as your difference not much. Also, both of them significant, but maybe in my result it's not much different, right? Maybe in other result different problem, right? It's just still a little bit different, right? Okay, so this one will guide you how to choose between the models. So if you want to see you want to try to reanalyze, right? You can try to shorten your cross section become 8, for example. Then you can compare with different individual firms. Maybe you'll come up with different result, because once you take up one firm, for example, from your result, for example, big firms, right? When you take up one big firms, the result might change. This is called outliers, right? Outliers means a difference from the rest, right? Because you cannot put them inside there, even though you take into account them, but you take it out, the result will become a bit different. There is another story under the cross dependency, whether they will affect each other or not. Okay, so that's the things, right? Yeah, here, statistic. So you can say, yeah, this means that coefficient, random effect are much more consistent as well as efficient, right? Efficient. So that is the story behind. Actually, what's the difference between efficient and consistent? I think in my previous, I think I got talk about the consistent, right? What's the difference between consistent and efficient? Yeah. So different, consistent, efficient are two different terms in the econometric. So maybe I can talk about this efficient first. Efficient means that minimum variance. So sometimes we say still remember the OS. How we get the OS is minimize the residual sum of square in such a manner in order to get your efficient parameter estimate. So the efficient here means that is minimum variance. Minimum variance. So actually, in another way, your parameter estimate is very close to your close to what we say the errors lah. Is actually minimum lah. That's called efficient. That's called efficient. We have a difference with the predicted and the true value. So what in another way is minimum variance as compared to the other estimator. It's talking about the variance, minimum variance as compared to other parameters. So that's called efficient. Now how about consistent? Consistent means that the coefficient, when you, because you still remember, you were asked, right, how big, consider big, right, for the sample size. Because in the econometric, we prefer the enough sample size. The bigger, means the larger, the better, right? Because the more information you put inside, it will increase your reliability of the result. Why? Because in the statement, he also mentioned that in order for you to get the consistent estimate, your coefficient actually will become getting closer to your true parameter estimate. But what we estimate actually is a sample, right? It's a sample estimate. But we cannot say sample equals to population estimate, right? Because of the time, because of the budget, right? Because of the expected budget time, right? So we just focus on the sample instead of population. So in order for our sample estimate to be accurate, so we need a consistent estimate. So if we increase the sample size, actually our estimate getting closer to the true population estimate. That is consistent. So that is the thumbs up. So in order for you to get the consistent and efficient, make sure you have a large sample size and also minimum variance. So that is the things that different between consistent and also the efficient. I should talk that one right before come to here. That's why you can see here. So even though reject, right? Reject, it means that actually random effect are consistent as well as efficient. Consistent as well as efficient here. So you have to elaborate the result, right? You cannot just copy paste the result, you have to elaborate. If significant of the result, what it means. Insignificant, what it means, right? So here, if you reject it, if your H0 is rejected, right? So random effect is consistent and efficient. Then if you fail to reject, then actually means that if you reject, right? Not reject, right? Then you consistent. Right? So that's the difference. So okay, so now I think this one we discussed last week also. Talking about different coefficient, right? Different coefficient, but equal error. error variance. So how to do that? In here, right? I can do it here also. So I don't think I can do it in this Gonville part 2 lah, because what let me try estimate. Go to quick estimate equation. I cannot do it here, because that's why I prefer to use the previous work file, because previous work files allow me to estimate them, to proceed to this estimation, to look at the different coefficient amongst these 10 firms. Because by using Gonville part 2 work file, it's very difficult for me to see the individually, right? Individually. So I minimize this one first. Yeah, this one. So when I go to estimate, right, I can see the cross-section specific coefficient, right? Like what I did last week, right? So I can see the cross-section specific coefficient. I can replicate the result here. So actually it's a different coefficient equal variance. So even equal variance, okay? So it means that there are no adjustment on the standard error, the error variance. So okay, so now I can estimate in such a way. So you can see I got a random, sorry, it's not. I just go no. So I can have this type of this. You can have a different equation, right? For each firms, you can see different equation for each firms. Then actually there is the estimation called similarly unrelated regression, right? That's another approach. You can go to estimate. Then from that, actually you need to choose the, let me see, the weighted here is a cross-section shape. Is a similarly unrelated regression, which used to account the cross-dependency amongst the firms. That's another approach. Another approach, cross-section shape. Yeah, cross-section shape. You go to OK. So this is the similarity. Sorry, I need to spell it correctly. It's called SHER. It's proposed by General Analysis Institute. Have you bought? Maybe not yet. So this one is unrelated regression. So it means that you use this approach to get rid of this the cross dependency, which is quite something like this issue when you want to tackle for this pattern. In the pattern estimation, we have to tackle. So some research they use this SHER. We call SHER estimate. SHER estimate is a similar unrelated. So you stack them together, then they do some adjustment, the estimate under the SHER. So actually it's under the physical GLS. Then they got introducing something like a metric here, to adjust it. So they come up with this new something like another estimation as compared to the fixed effect and the effect, as well as a pool OS. It's a different approach, similar unrelated regression. So you want to estimate? So okay, so why not, right? We use the previous version, right? Previous version. Can you tell me if without the GM, which model you prefer? You just estimate 9 firms, then you compare phase effect, random effect, pool OS, then you tell me actually which model you prefer. Are you still prefer random effect model after you exclude out the GM? Can you try now? You exclude out the GM. Exclude out the GM, just estimate with 9 firms. Are you still proceed Are you still have the same conclusion? You prefer random effect models? Can you do that? So that is the tips, right? So in the pool, right, you just exclude out GM. So are you going to use this? Are you going to can have the same conclusion, prefer random effect models? Okay? Is my statement very clear? Okay. I need to write down here, right? I also don't understand what I'm talking, sorry. Oh. Is it clear? So which model you will choose? So same model, same dependent, same independent, just without the GM, without the firm GM, just for 9 firms. So which model you will choose? Before we go back, can you answer this question? Not for next week, yeah, for today. Next week we're going to have a new discussion on the time series. On the panel, it's on the panel you need to write, right? So have you done? Which model you prefer? Not yet. So anyhow, so like that, okay? So which model you will choose? So same model but different entity. So I want to see the sensitivity of my result, right? For example, I want to see the sensitivity of my result, whether I escalate up my GM and I still choose the random effect models. Then I start to choose between the pool OS first. Pool OS is my pool OLS. This is my fixed effect model. So I run these two. Then I try to see the equality of the intercept. Then it's reject, right? So reject, what it means? Reject means prefer the fixed effect models, right? I would prefer the fixed effect model rather than the pool OS. Then how about my compare with the random effect together with the pool OS? Where is my Lagrange multiplier test? So in order for me to test, I need to use because I just found that, yeah, that's why there's a reason why I do not have a part. I will have a part 2 work file. In order for me to come up with a Honda test, Bush-Praghan test. So in my original file, I escalate out the GM. And then just with the 9 firms. With the 9 firms, I copy, and then I go to my e-views and put to my e-views, right? I go to File, New, Work File. So these are how I create the Part 2 work files, okay? So balance panel, and then annual, start date 1935, end date 1954, right? Number of cross section is 9. Only 9 cross sectional. Then I click OK. So I have a 9 cross section here. Then after that, I want to paste my data set. I just go to quick empty group edit series. So this is the something like we paste that time series, right? But this one is the 20 observed with the 9 individual. So you can see 1, 2, 3, 4 up to 9 here. Yeah, paste. So I have my series here. It means that for all my 9 sample, that's why I got my part 2, but that's why it's for 10 firms, right? But if you say, how about 8 firms? Yeah, we do it again. No? There is a difference as compared with the pool object. The pool object is much more flexible. You can select which one firm to be included or exclude out, right? There is a reason. There is a reason. But one of the limitation of the pool object, I cannot run this the Honda test. This Lagrange multiplier means that Lagrange multiplier test. So I have to introduce these 2 work files. So I can go to estimate equation that I did just now, investment, and then followed by my constant, followed by my CAP, and then VA out. Then I just click OK, right? Click OK because in the want to run this Lagrange multiplier is use the conventional pool OS. Then here we go to View, and then go to the fixed effect testing, omitted random effect. There is a Lagrange multiplier. Then you can see, right, different structure, different statistics available. So you click on the Lagrange multiplier. So this is my test statistic for my 9 firms. So based on this result, right? Based on this result, all my statistics again significant, right? Significant. So significant means what? Means that I cannot ignore the individual effect. So I cannot ignore the individual effect. So I have to select the random effect models. Because the first now here is no effect. So you reject, because reject, right? Reject the first now. So reject no effect. So actually there is an effect. So I will choose the random effect model. So that's why random effect model is preferable as compared to the full OS. Again, this one choose Quicksum fact, right? Based on the equality of this intercept, and based on Lagrange multiplier, choose random effect. So between random, between fixed, which one you will choose? So under this scenario, I need to use the Hausman test to see the efficient and also consistent, right? Whether which one is preferable, whether there is the assumption for this whole or not whole, right? Random effect model whole or not whole, whether there is correlation between individual effect together with the regressor. So Hausman test, again, p-value is lesser than the alpha value, which is for example 5%, 0.05. So you fail to reject, right? Fail to reject. So once you fail to reject, again, IEM more reliable because it provides much more consistent and efficient estimate as compared to the random effect models. So again, we just 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. With these 9 firms, I still choose the random effect models. So is it result same or not same? Let me see. This with the 9 firms, right? I choose this random effect models. Oops, what is this? This 9 firm. How about with the 10 firm? Random effect. Are they same? Are you packing to go back home? I can hear the sound. Okay, yeah, thanks. So okay, so now, even though with the question mark, right, it's just different profile only. So are they same? Yeah. Same or not same? Different, right? Maybe wait, I should use the same file, right? Okay. Then only comparable. I want to see this one. Hey, with the no. 9 from this one. Here. This. Oh, same, surprise, right? So when I remove my GM, right, what happened? You see, the constant means that the mean for the C change, right? And then the stroke coefficient for the CAP and also VAL totally different already, right? With this 9 and together versus the 10 firms here. Even though with the random effect models, there are 2 different results, right? So that is the interesting part without the GM, right? And then but both also significant, right? Both also significant. Yeah. Okay. We can compare. Because when you see, right, with the similar, like your friend just now also asked about the adjusted R square. With the similar independent variables, this adjusted R square 0.367, but this adjusted R square 0.76. I hope I did not estimate it wrongly. I think I'm correct, right? Okay, I think that is the things I want to share to you today. So you can go through the journal article I shared last week, right, to see how the researcher elaborate the result much more in details. Okay. So okay, that's only for my side. If any question, no question, then see you all next week. Next week we're going to discuss about the panel unit test, right? So we have an extension from the 10 series unit test, then we extend to the panel unit. So and then for this fixed effect random effect, we stop here. Then after that we talk about the panel unit rule, then we'll go through the panel